Creating beautiful renders of molecular dynamics just got a lot easier. Thanks to a groundbreaking add-on created by Brady A. Johnston, molecular dynamics scientists can benefit from all the rendering powers of Blender 3D in a few clicks, and it runs really smoothly as well. To get started, we need to install the add-on. To do this, head out to this link in the description, download the zip file and save it somewhere in your computer. Now, in Blender, go to Preferences, Add-ons and hit Install, and just navigate to the zip file. Activate it, and then finally install MD Analysis. Okay, now, if we go to this Scene Properties tab, we have this Molecular Nodes drop-down menu that has been added. Oh, and by the way, a few months ago I have made a tutorial on how to import PDB files into Blender. Well, that can go straight into the trash now, because this add-on allows you to do it directly and has a ton of features to style them nicely right off the bat. Okay, moving on. To import MD simulations, we come to this little drop-down menu and select MD. You need to provide your MD data into two files. One topology file in the PDB format for the first frame of your simulation, then a trajectory file in the DCD format, which has the information on how the atoms move throughout the simulation. If you don't have them in such a format, you can get them using the free software VMD. Load your simulation, then export the first frame as a PDB file. Then select all of the frames and export them into a DCD format. Once you have those two, load them into the tool. And there we go. We have them here. You can see that they are imported as points. Now, if you want to see them, I recommend getting into the rendered mode. Then in the render tab, switch the engine to cycles and use your GPU if you have one. Now, you can hit play and watch the animation in real time. In this example, by default, all the atoms are black. In your case, colors might be appearing correctly already, but regardless, I will show you how you can modify them. If you come to Geometry Nodes tab, we can see how it all works. If we come inside of this group, we see it uses this atomic number attribute of your data to control the colors. However, in my case, I don't have this data. Fortunately, as long as you have something in your dataset that can define which atom is what, you can use it to control the color. In my case, I will use the atom_types, which has values from 0 to 8. So I change the named attribute, I'll unplug all of this for simplicity, then I set these compare nodes to 0, 1, 2, 3, 4, 5, and then I need to use Shift D to duplicate the nodes 6, 7, and 8. And then copy the plugin setup basically. Now you have full control over the colors of each individual atom type. Now we'll exit this group. You can also use the same principle, that is using a named attribute into a compare node to separate a particular atom type from the rest. And this allows you, for example, to tune the size of individual atoms or to make them selectively disappear for clarity. If you noticed in my initial example, I used a different material for some atoms. Especially for the gold surface, I think it looks cool. If you try to modify the material in geometry nodes, it won't actually work. It's because a point cloud can only have one material. However, if we go to the shading tab, we can edit the material. One shader would be the regular color, and then the other would be a metallic golden shader. I then use a color ramp node to isolate the parts I want to change. Now this might not be the best method, but it works. And then I use the output to control a mix shader node. And there we go, my gold surface looks like it's made out of gold. A typical full high definition video is composed of 2 million pixels. You need the values of red, green and blue for each pixel, therefore that makes about 6 megabytes of data per image. So that would mean that a 10-second clip at 30 images per second would get a 1.8 gigabytes file. And this is why most videos have amazing compression algorithms that can make the file size of video files over 1,000 times smaller. Why am I speaking about this now? Well, molecular dynamics videos are typically the type of content with all the independent elements moving around for which compression algorithms will have a very hard time. The result will look fine inside of Blender, but when you upload it to YouTube, the quality might get absolutely wrecked, turning your result into a big mush of pixels. Working around this is basically striking a balance between the number of elements you want to show at once and their quality. You can adapt this using a clever use of zooms, depth of field, or simplify the colors, or selectively hide certain atoms. That way, you can minimize the work that the compression algorithm has to do to reduce file size, and you will protect what you really want to show on screen.